All right, so in chromatography, everybody, okay, there's always two parts of every chromatography experiment. Okay, you always have what is called the solid phase, which is not moving, the paper, right? The paper is the solid phase. You then always have some sort of aqueous phase, a liquid-like phase, okay? In our case, we're using distilled water, okay? Note, it doesn't have to be water. In the lab, you're gonna pick between like 5 different things, okay? Just depends on what you're going for. The idea here, once again, is chromatography separates them based on what they stick to. The idea is some of the things are going to stick hard to the paper, others are actually going to stick to the moving liquid. And that's when you get the separation. Okay, so here's my rough analogy. It's a little better for you guys than it was last period because I had one test run. But I thought about this when I was trying to sleep last night, so it's still kind of important in my head. Okay, but play along with me here. Okay, let's pretend, everyone see this like strip of like open no students? Okay, we're going to pretend that this strip represents the paper. Okay, and all the students who are directly connected to it, you are like the molecules of the paper. Okay, so let's say first example, I'm water. What is causing the water to travel along the paper?
Osmosis.
Cohesion.
Go to chemistry.
Cohesion.
Deeper, Grayson.
Repulsion from the surface tension.
Deeper.
Hydrogen bonds. Electron bonds. Hydrogen bonds? Hydrogen bonds.
Electrons.
There's an interaction, right? There's an interaction between the water molecules and the paper molecules, and so the water kind of gets passed. The way I think about it is it's like bouncing between hydrogen bonds. This particular paper has hydrogen bonding on it, and so it's jumping from a hydrogen bond to a hydrogen bond to a hydrogen bond, and so it's traveling up the paper.
Is this capillary action?
It's the same reason why capillary action happens. Yep.
Okay.
Yep, because it goes back to the forces. Okay? All right. Everyone got that visual? So that's why the water's traveling. Now, raise your hand if you use the marker where the dot is separating. Raise your hand if that's your half of the table. Okay? Someone tell us, what do we see happening in that chronograph so far?
Colors as it goes.
What colors can you see? So you definitely, so normally you should see some blue, and which one's the farthest? Blue, and then sometimes if it's run long enough, you start seeing a little bit of yellow in the middle, and then there should be some red. Okay, the yellow's the hardest one right now to distinguish, okay? All right, tell me this now, everybody, ready? If, okay, so I'm the blue part of the mixture. What does it tell me about that blue ink, being that it traveled the most with the water? What does that tell me? What can I claim about the blue ink, AJ?
It's expressed the water, so it's probably highly polar.
Good. Since it traveled a lot with the liquid phase, there must be a stronger interaction with the liquid than there is with the paper. Okay? Now raise your hand if you have the dot that appears to be doing nothing. Okay, the other half of the table. What does that tell you, though, about the forces of that ink? Go ahead, Leslie. Yes, I know that they have a stronger adhesion to the paper, hence their IMFs.
Yeah, I was gonna say.
Good. You'll start to see one color come out. I don't know if we could yet. Right? But that tells me that the blue and the red in the permanent marker don't have an interaction with water, but you should be able to start seeing a little bit of yellow. So the yellow inside the permanent ink does have an interaction with the water. So it's all about what will it stick to the most. Okay? So in our chromatography, once again, they're separated by their IMFs. Okay? The idea is, and once again, it's not a polar travels fast or non-polar travels slow. It depends on what you're using. It's that like sticks to like. Polar things want to interact with polar things. Non-polar things interact with non-polar things. Okay? If the solid is polar, once again, the solid's the paper, then the polar component will attract to it more than a non-polar component. So whenever you're dealing with chromatography, that's the first thing you should always do is figure out, okay, what is flowing? Is it a polar solution or is it a non-polar solution? Because otherwise your results would be opposite if you use the opposite kind. Yeah?
Why are we not doing the chromatography the other way, where the water is like poured on the top of the paper and then poured down? Like, you know, it's what does that.
I've never done a chromatography where it comes from the top.
I'm just wondering.
Or like why in general?
Yeah. Is there like a specific reason with how the water interacts with the paper or anything?
I think this is just an assumption, AJ, because I've never really thought about that before. But my thought would be something about that the gravity of it could cause the water to travel too quickly and not give the molecules time to be pulled apart. Where this is like a slow, like it takes like it goes fast in the beginning, but now it's like kind of going pretty slow up the paper if it's still moving at all. Where if you like went from the top, like the water would just go quickly and you wouldn't actually see that clear distinction. Does that make sense? That's my guess though, but I don't know. I never thought about it that way. All right, let's take a look at an example of an AP question to get our minds thinking about this. Okay, so the student is testing using paper chromatography. They have 3 pure dyes labeled A, B, and C, and some unknown sample. The unknown is either A, B, or C. Okay, the student prepares the chromatography chamber shown above on the left by putting a drop of each dye at the indicated position. Note this, highlight this. The paper is a polar material. Okay, pay attention to, okay, where's my polarity, where's my non-polarity? Okay, so the paper is polar and the solvent is non-polar. Okay, so we're using a non-polar solvent. Okay, and then this is when it's developed. Okay, so here's your before, here's your after. The question says which dye, A, B, or C, is the least polar, and then justify your answer in terms of the interactions between the dyes and the solvent or between the dyes and the paper. So this is a great reminder if it says justify in terms of, this has to be part of your justification, right? Like make sure you're talking about those interactions, otherwise even if your logic is right, you won't get full points, okay? All right, let's give you 2 minutes. I want you to try to answer it on your own for the first minute, and then after a minute's up, I'll let you discuss with your table, so that way you can get your brain to think on its own first. Once again, A, B, or C, which one is the least polar? I'll even give you a hint, it's not A.
What?
In case that was what you were wanting to know. Oh, that did not work, Hayden. How did that jump off like that? All right, you can keep writing on your own, but if you want to inquire of your neighbors what they wrote, you're allowed to talk to them now.
I said C. Also
I said C.
The paper is polar, so since the paper is polar, it being B would be the most polar. Because really? B would be polar. C would be like so it's gonna stay yeah, so like things found closer to the bottom are more attractive to them. C is like this polar.
They still have a positive and negative going on, it's just not very strong. But all positive and negative things are weak, right?
Yeah, he is. And he called out Chase. That was so funny. He called out Chase yesterday.
Okay, ready? On the count of 3, you're going to show me with your hand, don't say it. You can show me A. I told you it was A, so don't show me A. B or C. Okay, on the count of 3, show me your answer. This is a B, this is C. Ready? 3, 2, 1, show me your answer. What is a B? It's not a B. Oh dear. Okay, this is a C, and that is the correct answer. You can have a smiley face. Do I have someone? I know, just put it in your notes and I'll transfer it over. I forgot to print them off. Does someone read their justification for us for an extra smiley? Let's hear it, Cameron.
Alright.
Okay, everyone listen to this, please.
So dicey would be the most would be the least polar. Sorry, I wrote that wrong. The solvent is non-polar and dicey is the travel farthest step of paper and interacts most with the solvent. Because non-polar molecules interact best with other non-polar molecules, it would be the most useful.
Beautifully said. How smiley face that? Do I have one more? Just here, same thing, but in different ways of saying it. Mary, go ahead.
Dicey is the least polar. Molecules stick to molecules with a similar polarity to themselves, so because the dicey travel the farthest and stuck more to the non-polar solvent, that means that C must be have the same polarity as the solvent, which means that it's not polar.
Perfect. Good. Have a smiley face. Okay. Questions on this? So this kind of understand that molecular level, what's going on in chromatography. Okay, open up your lab book. I think it's page 30, 27? What is that? Nope, it talks about sticky molecules. 30? 30. Turn to page 30, everybody.
They like carbon.
They also like red 40.
There also can be things that cause
Red book is
polarity
green.
shifts. More
Made so
polar
many like dye, ways to dye. And then in the end, it's so
You're going to try to figure out what gives you the best separation. You have different solvents to test. See, like, yours, like, it does give us a good red separation. It will give us a good yellow separation, right? His only gives us a yellow separation. It's kind of like what Good question, Marilyn.